All right, so for this video, we're going to be talking about resonance and then the geometry and polarity for the different molecules that we see. Okay, and this again through covalent bonding. This will be a more lengthy video just because we do need to go through all the geometric shapes that we see. Okay, so let's get into it. All right, so last video, we talked about writing Lewis dot structures, and there's going to be times when you're going to see some resonance. And what a resonance really is that you can do multiple shapes or multiple forms with that Lewis dot structure. So again, if we're looking at SO3 here, I believe that's sulfite, there can be multiple ways in which you can have that double bond. And so if we look at here we see that there are two single bonds between the sulfur and the oxygen atom, but there is also a double bond. So we can do this in multiple ways, and because of this multiple bonds or drawn in different ways, this is called the resonance when there's more than one valid Lewis dot structure. And again, I could have the double bond here, I could have the double bond here, I could have the double bond here. Again, all those are acceptable because of the resonance that we see. All right. When you do have a resonance, make sure that you do draw all the structures and you connect it by double arrows to show that, yes, one of these or all three of these are acceptable for the Lewis dot structure that we see. All right. There are exceptions to the octet rule. There are some molecules that do not follow the octet rule. Again, ions are molecules with less than an octet. So again, hydrogen is a very good example of that. Ions are molecules with more than 8 valence electrons. That again would be an expanded octet, but for the most part, we will use the octet rule when doing the Lewis dot structure, with those exceptions of hydrogen and other elements that we see. And then the non-octet structures that we see. So beryllium, what we see is that it's stable with only 4 shared electrons, so 2 bonds. So again, the 2 hydrogen bonds that you see, again, that is stable. Boron and sometimes aluminum also share this non-octet rule. And again, it's stable with only 6 shared electrons, so 3 bonds. All right, on to geometry and polarity. So again, what you have seen are different shapes of how different structures are created. And again, we're going to go through what each one looks like and how each one is being shown. All right, so the Vespar theory. This deals with the valence shell electron pair repulsion theory. And essentially what this is meaning is that the electrostatic repulsion between valence electron pairs surrounding an atom causes these pairs to be oriented as far apart as possible. What it's pretty much saying is electrons don't want to be next to each other. So they will get as far away from electrons as they can, possible at least. So this will help us predict three-dimensional geometry of molecules. It can also determine the angles of bonds. And again, we will get into that more in class, seeing the different geometry of different things, all right? All right, so the tetrahedral. What we see with the tetrahedral, this will be our first molecular geometric shape that we're going to look at. It has 4 atoms that are bonded to a center atom with 0 lone pairs. Okay, so again, we're looking at carbon here. We see that there's 4 hydrogen atoms that are binding with that carbon atom. Again, that central atom. So this is seen as a tetrahedral. All molecules with a center atom that obeys the octet rule are based on this geometry. So an example, again, would be carbon tetrahydrogen. And again, we look at the angle for the different angles that we see here. Again, 109.5, we'll see that between all of the different bonds. The next one that we talk about is trigonal planar or trigonal pyramidal. And so what happens here is that there are 3 atoms bonded to the center atom with 1 lone pair. And the biggest thing is that with trigonal pyramidal. Again, you're having this one lone pair here while the other ones are bonded. So again, very, very similar to trigonal or tetrahedral, sorry. But again, the way you guys can think about this tetrahedral, so that's 4, again, bonded here, while trigonal, that'd be 3. And then pyramid, again, it makes a pyramid with that lone pair. And again, we see that the angle between these are 109.5. Our next one is bent. And so this is when two atoms bonded to a center atom with 2 lone pairs of electrons. And again, this is called a bent because of our Vesper rule. Again, it's telling us that electrons want to stay away from each other. So this is causing the bend of these 2 hydrogen atoms to not be, again, 180 degrees. And again, we have our 2 lone pairs here. Example of this would be H2O or water. Trigonal planar is 3 atoms bonded to the center atom with 0 lone pairs. So again, this will not create that pyramid effect that we see with trigonal pyramidal. And so here we have more of a triangle shape or trigonal planar. So again, we see boron here, trioxide or trihydrogen. So 120 degree angle between the 2 bonds, or all the bonds. Molecular geometry bent. This is when 2 atoms are bonded to center atom with 1 lone pair, and this bent is called a bent molecule. So again, what we see here with ozone, again, we have 2 oxygen atoms binding to essential oxygen atoms, and you see that lone pair here. Again, with that bend, it's causing this 120 degree angle, and again, it's the electrons, they want to stay away from each other. Molecular geometry, we're looking at linear here. 1 atom is bonded to a center atom with 3 lone pairs. So again, we see this with hydrogen monochloride. So again, we have the 2 pair here, and we have the 3 lone pairs. Double bond, this would be 2 atoms. Again, we have double bond here, and we have 2 lone pairs for each one. Triple bond, this would be between 2 atoms that have a triple bond. Again, they would have 1 lone pair each. 2 atoms bonded to a center atom with no lone pairs. We see this with CO2 just because that the oxygen does not have any lone pairs, and carbon dioxide, I don't know what I was thinking. Carbon's good with the double pair or double bonds between the 2 oxygen atoms. And again, they're fine. Everybody's fine because their octets are filled up. So again, here is a look at all the different shapes that we see for the different bonds that we see. Okay. And then here's a nice summary of the geometry of it. Here's a nice chart. So number of atoms bonded to the center atom, number of lone pairs on the center atom, and then the geometry of species. So if you follow all of these, this will lead you to the name of that geometry. And again, this should be on your notes. If not, you will write this in. And then we'll get into molecule polarity just real quick. With molecular polarity, again, this is talking about how aggressive or how much electronegativity difference there is between 2 elements that we see. So just like bonds can be polar and nonpolar, so can molecules. Molecular polarity starts with the bond type. The problem is that polar bonds don't always give you a polar molecule. And again, it depends on the symmetry of the molecule. So perfect symmetry, again, symmetrical with all outside atoms, the same element. They can neutralize the polarity to give a nonpolar molecule. Polar molecules have an unequal distribution of charge. They must have a lone pair.
Please report to the attendance office. Cassandra McLaren, Peter Bracken, Austin.
All right, Jacobson. I will try to get through this. And they must have a lone pair. Nonpolar molecules have an equal distribution of charge. It either has no lone pairs or perfect symmetry. So again, if we look at water, that is polar because, again, unequal distribution of charge. There's a negative charge near the oxygen while the hydrogen are positive. Ethane here is nonpolar, again, equal charge, has no lone pairs or perfect symmetry. Okay, so nonpolar covalent, perfect symmetry, yes or no, and a molecular type nonpolar. Polar covalent, perfect symmetry, yes. Molecule type nonpolar. Polar covalent, perfect symmetry, no. Polar, yes. All right, so every nonpolar covalent bond is going to create a nonpolar molecule type. Polar covalent, if it's perfect symmetry, again, nonpolar. And then polar covalent with no perfect symmetry, again, we're looking at a polar molecule. And then with polarity, a molecule's polarity is determined by its shape and distribution of electrons. Geometries that have perfect symmetry are tetrahedral, trigonal planar, and linear. And so, in order for the molecule to be symmetrical, all of the atoms bonded to the center atom must be identical or have the same number of lone pairs. So, again, this goes over the geometry and the polarity that we see with different structures.